It's easy to forget, the further we go into algebra, that all of the rules and the ideas and the concepts that we are working with are essentially the next level of abstraction from numbers. Everything you learned that works when you're doing arithmetic, when you're adding, subtracting, multiplying, dividing, dealing with brackets, all of that still applies when we're dealing with algebra. In fact, if anything, sometimes it's easier. When we're multiplying things algebraically, we just write the two expressions next to each other. In numerical form, we can get bogged down in the detail. In algebra, we're looking at a higher level, a generalization, but we have to remember that if it works with numbers, it will work with algebra. Algebra is designed to give us a stronger tool which encompasses everything with numbers, but lets us have more of a bird's eye view of the structure and the underlying connections between things that we couldn't necessarily see so clearly if we were zoomed in on one specific value. For this reason, if you're dealing with some kind of algebraic simplification and you're not sure if a step you've made is valid, a good tip is just to substitute in a few numbers. If it's the same numerically for some particular value of x, let's say, then chances are it's going to be equivalent algebraically. If it's not the same numerically, then it's absolutely certain that it's not the same algebraically either. The two expressions, for them to be equivalent, need to be the same for any value of x. So if you can find even one value of x where it doesn't work, then you've demonstrated that your two expressions are not equivalent. Now, there's a number of important properties that we're going to look at. You have come across them before in various different guises. And the first one is known as the distributive property. We sometimes use the phrase multiplication is distributive over addition, which means if you're adding things and then you want to multiply the result by something, you are perfectly at liberty to multiply each of the two separate terms to get by the scale factor first and then add the result. This is a really important property, partly because of when it works, but in many cases because of when it doesn't work. It works for multiplying. It does not work in general for other functions. If you've got something plus something and then you want to square the result, that's not the same as adding the squares of the two original numbers. B plus C squared is not the same as B squared plus C squared. If you have sine of A plus B, that's not the same as sine of A plus sine of B. Most functions don't behave in this way, but it's useful that multiplication does. You've used this ever since you learned how to multiply numbers like 3 times 17. If you're working out 3 17s, you probably do 3 10s and 3 7s and add the result. Algebraically, the most common place you come across this is either in expanding brackets or in factorizing. The next key idea is equivalent fractions. Anytime you've got any fraction in any form, you can convert it to another fraction which is worth the same, equivalent, equal value, by simply multiplying the top and the bottom by the same scale factor. That number that I've written out here as k could be anything. It could be positive, negative, it could be some fraction itself. You might be multiplying the top and bottom by a half. That's how we turn 6 over 8 into 3 over 4, for instance. And the crucial thing about this is that it does not change the value of your fraction. If I were to say I'm going to double my fraction, then that means I'm multiplying the fraction by 2, and I'm expecting to get a number that's twice the size. So if you have 3 sevenths and you multiply it by 2, you get 6 sevenths. If, on the other hand, you want to multiply the top and the bottom both by 2, really what you're doing is 3 sevenths times 2 over 2. And because 2 over 2 is 1, you're not changing the value of your fraction. This should be something that you're listening to and thinking, yes, I know that all makes sense. And it does for numbers perhaps, but you need to make sure that you can apply the same ideas even when you're dealing with a really messy algebraic fraction. The last thing is the collecting of terms. Here you can essentially see a fundamental idea behind adding fractions, which is that if the two fractions are the same type, you can simply add the numerators. If you've got a tenth and another 2 tenths, then you're looking at 3 tenths. They're still tenths. We haven't changed the size of the slice. You've been given a slice of pizza followed by another 2 slices of pizza. They're the same sized slice that they always were, but you now have 3 of them. This is equivalent to saying that AX plus CX equals a plus c times x. So in a way, it's the same as the distributive property, but it's been written in the form of fractions so that we can see it in that way. We can distribute the division across the a plus c by working backwards from a plus c all divided by b to a over b plus c over b. I would call that dividing through by b. So each of the separate terms on the numerator is divided separately by the entire denominator. Doesn't work if you try flipping the thing around. If you have b over a plus c, you certainly can't write it as b over a plus b over c. Things don't work that way. But if you've got a fraction with a denominator and you've got two separate terms on the top, you can separate that out. What I'd like you to do first here is evaluate the following numerical expressions and to think carefully as you do it which of these three properties, maybe more than one of them, which of these properties you're relying on in order to effectively combine these terms. For some of them, it might just be a trick to make the process easier, like the first one. For others, it'll be a fundamental idea that we need to understand and be aware of in order to allow us to deal with the problem. You might want to have a go at the last one, but you'll need to remember the definition of the factorial function. 10 factorial over 3 factorial, 7 factorial. There is a nice way to calculate the value of this. Again, you won't need a calculator. It's not as tedious as it might seem. You will need to think carefully about what can cancel out. So pause the video, see if you can answer those 4 questions, and when you're ready, we'll talk through them. So the first one, hopefully you've noticed, instead of having to work out 98 lots of 52 and 2 lots of 52, we don't actually care about those individual values. We care about the sum of those two. By using the distributive property, we can put them together. 98 52s and another 2 52s is 100 52s. And out pops 5,200. For the next bit, we're going to make use of the fact that we can collect terms. These are all 20ths, so we can add them. 1 20th, another 2 20ths, and so on, gives us a total of 10 20ths. And then we're going to make use of the equivalent fractions concept to cancel that down. We're multiplying the top and bottom by a tenth in this case, which you would probably usually think of as dividing top and bottom by 10, which is equally valid. Not only can you multiply fractions by 1 in the form k over k, but you can divide fractions by 1 in the form k over k. You can divide the top by something and divide the bottom by something, and as long as the two somethings are the same, the fraction will be equivalent. For the next one, there are a few long-winded ways of doing this. The most efficient way is to use a common denominator. 40 and 50 can both be written can both be scaled up, rather, to give 200. 40 and 50 are both factors of 200. In fact, 200 is the smallest number, which 40 and 50 are both factors of. So it's the lowest common multiple. And if we make use of that, we don't have to change the numerators quite so much as if we were using a more long-winded method. We scale up the top and bottom of the first fraction. So we're multiplying by 5 over 5, which doesn't change its value, but does give us 35 over 200, an equivalent fraction. And the second fraction gives minus 44 over 200. If we subtract those, we do get a negative number. Usually we write this either with the minus sign in front of the fraction or potentially in the numerator, but we wouldn't leave a fraction with a negative sign in the denominator in general. For the last one, if you manage this one, well done. There's a nice trick here. We have to notice that because 10 factorial is the product of all of the integers from 10 down to 1, it can be written as 10 times 9 times 8 times 7 factorial, which is all of the integers from 7 down to 1. And that means that 7 factorial cancels out. And we're left with just the 3 factorial, which is 3 times 2 times 1, or just 3 times 2 on the bottom. And we have 10 times 9 times 8 on the top. We can make life even simpler if we break things down into their component parts. It's not strictly necessary in this particular case to turn things into prime factors, but we'll revisit this idea of having things broken into their most fundamental factors when we're dealing with algebra in a moment. So it might be helpful to think of how this convinces us we've simplified as far as we can. We've got a factor of 2 on the top and the bottom. In fact, there's 4 2's multiplied on the top. And there's a factor of 3 on the top and the bottom. There's 2 3's on the top. When we cancel down, everything in the denominator cancels down to 1, so we're dividing by 1, therefore all we're left with is the 2 cubed times 3 times 5, which is 120. Incidentally, you might have recognized that 10 factorial over 3 factorial 7 factorial. It represents the binomial coefficient, or a term in Pascal's triangle. You may or may not have come across this yet, but it is a way of counting how many different possibilities there are for choosing 3 objects from a collection of 10. So let's say you've got 10 students in a room and you need to select 3 of those students to represent the school in a competition. Then there are 120 different ways of choosing 3 students. If we choose student A and then student B and then student C, that's the same combination as student A and then student C and then student B, because you've ended up with the same 3 students. So combinations needs to adjust for the fact that the same 3 students chosen in a different order is still the same 3 students. We only want to count that combination once. If you're curious, this little animation will show you all of those 120 combinations. Every single way of choosing 3 students from a collection of 10 students. And you can see there's going to be a fair number of them. You can see the systematic way it's produced, and you might want to think about why all the factorials appear in this particular calculation. Now I'd like you to do the same thing with these algebraic expressions. See if you can write them in a simpler form. Just like with numbers, we find it helpful with algebraic expressions to have a bunch of separate fractions written as a single fraction, or to factorize something which could be written as a product of 2 or more things. Or if we have a single fraction already, to simplify it, to write it in its most simple form. So try these 4 questions, write them as simply as you can, and think carefully as you go about which of the 3 key properties you're making use of at each stage. So for the first one, we can pull out 2 common factors. X is the highest power of x that appears in all 3 terms, and y is the highest power of y that appears. So we can get xy as a common factor, and y plus xy in the bracket. For the next one, these 3 fractions all have different denominators, so they cannot directly be added. We can't just collect terms yet. First, we need to take advantage of the equivalent fractions concept so that we can write all the fractions with the same denominator, and then we can add the numerators. Now we could use xy cubed, that's just the product of the 3 denominators, but because y is a factor of y squared, it's a bit like if you're adding a 10th and a 20th. You don't need to turn your fractions into 200ths, you can turn them both into 20ths. And in this case, we still have the x we need to incorporate, but xy squared would be a more efficient choice. If you've chosen to use xy cubed, you should find that at the end you can simplify down, just like if you add a 10th and a 20th by thinking of it as 20 200ths plus 10 200ths, you'll get 30 200ths, and that'll simplify down at the end to 3 20ths anyway. So it doesn't necessarily cause a problem, it's just less efficient if you choose a common denominator which is not the simplest possible common denominator. So with this one, I've multiplied the first fraction by 1, obviously, but in the form y squared over y squared. The last fraction has been multiplied by x over x, so top and bottom have both been scaled up by a factor of x, and the middle fraction needed multiplying top and bottom by x and by y. And once all the denominators are the same, we can add the numerators, and we keep the denominator the same. We're combining the terms because all of the terms are a multiple of 1 over xy squared. For the next one, we need a bit of trickery. In order to see if this fraction can cancel down, we need to know what the factors of the top and the bottom are. Now the bottom doesn't have any other factors other than what it is. It's a little bit like a prime number. If you've got a fraction like 6 over 13, you could factorize 6, you could break it into 2 times 3, but 13 can't be broken apart any more than what it already is. And in the same way, x add 2y is a fundamental algebraic expression that cannot be broken any further. You could pull out numerical factors, but algebraic factors, this is the only one we have really. On the top, however, we've got a quadratic. It's a quadratic involving x squared and y squared, but if you look carefully, you might notice that we have the difference of two squares involved here. X squared minus 2y squared. That's how we get the 4y squared term. And if you have a difference of two squares, there's a quick and easy way to factorize. We can turn it into x plus 2y times x minus 2y. And as soon as you've done that, you can see that there is a common factor on the top and the bottom. In fact, the entirety of the denominator is included within the numerator. So this is like having 50 over 5, and we can divide through by 5 top and bottom, and that's equivalent to simplifying your fraction. We get x minus 2y over 1, which is of course just x minus 2y. And the final fraction. Lots of possibilities here. Some people will cancel the x's. That's a common phrase we get. Cancel. We use the phrase cancel mathematically to refer to eliminating perhaps two things usually, which if neither of them were there would give the same result as if they were both there. If you are adding 17x and then you subtract 17x, then perhaps you can cancel those two terms and just not do either of the two things and everything will be fine. If you double your income and then you immediately halve your income, well, you're back where you started. And we can cancel things in the way that we did on the line before by crossing them out because they appear on the top and the bottom, but it's a little safer to think about why you can cross them out. And it's not just that they appear on the top and the bottom, it's that they are factors of the entire numerator and denominator. It's only if you can write a fraction in the form Ka over Kb that you can cancel the k's. The answer for this one is exactly the same as the question. If you try to do something else, perhaps you cancelled the x's. Effectively, what you would have been doing if you cancelled the x's, if you crossed them out, you wouldn't have been dividing by a common factor. You would have been subtracting the same thing from the top and bottom of a fraction. And if you want to check to see if that's something valid, test it with a fraction. Think about a simple one like 3 over 4. What happens if we take away 1 from the top and the bottom? We get 2/3. Is that the same as 3 over 4? Do it again. We get 1 over 2. Is that the same? Is a half the same as 3 over 4? You can see that adding and subtracting the same thing from the top and the bottom does not give you an equivalent fraction. If you'd done that, you might have gone a step further. You might even have cancelled out some y values. You might have 4y over 3. That's quite a common answer for this. But there is no simpler way of writing this particular fraction than the way it's been written here. X add 4y squared over x add 3y. You can't split it because the denominator is one single term. There's an important principle at play here. We need to know when we can simplify or convert or change things and when we can't. Puts me in mind of the old theologian's prayer. We need to know what we can change. We need to know that there are some things we can't change, and you need to be just as careful to not oversimplify things that cannot be simplified algebraically. In the same way that you need to know how to simplify the ones that can, you've got to learn to recognize the ones that are already in a form that cannot be made any simpler and not do something illegal operation-wise to a fraction or an algebraic expression just because you feel like there should be some nicer way of writing it. Sometimes there isn't. Now, when we're simplifying fractions, any fractions, we have to have a common factor. We need to have something we can divide by on the top and the bottom. I'd like you to have a look carefully at these three examples and see which of them you think has used a valid process to cancel down the fraction. They all seem to turn into very simple things: a third, minus 1, minus 2/3. Which of them are valid simplification steps and which of them are not? I've deliberately dressed this up with a bit of trigonometry in here. You don't need to know very much about sin x and cos x. You just need to understand that sin x is the same as sin x and it's not the same as cos x, and that's all for the purposes of this. But think about whether you can identify any common factors, and if you can you apply the rules that we already have for fractions to see which of these might be valid and which ones not. Another thing you might want to have a go at, if you've solved the first three, have a think about this false cancelling example. Sometimes it's possible to do something incorrect and get what appears to be a correct answer. 16 over 64 certainly is equal to a quarter, but the reason it's equal is not because you can cancel out the sixes. See if you can find any other examples of fractions that do a similar thing. Maybe you can write yourself a program that finds numbers that do this. So with these three we've got on the left, let's talk these through. The first one, 5 sin x minus 2 cos x on the top, 15 sin x minus 6 cos x on the bottom. This one is a valid simplification. The reason for that is that 5 sin x minus 2 cos x is a factor on the top and the bottom. In fact, if you pull out the highest numerical factor from the denominator, that will be a 3. You can pull out a 3 and call it 3 lots of 5 sin x minus 2 cos x. And then you can see that the top is exactly a third of the size of the bottom. We can cancel out the entire chunk of algebra from the top and bottom, and you'll be left with 1 over 3. The next one, they don't look quite so similar, but if you look closely, you'll find that 5 sin x minus 2 cos x and 2 cos x minus 5 sin x are very, very similar. In fact, you can pull out a common factor here, not a number like 3 or 5, because 2 and 5 are co-prime. They share no common factors, except the trivial ones. Everything divides by 1, and by the same token, everything divides by minus 1. So you could pull out a factor of minus 1 from either the top or the bottom, and that would leave you with the contents of the bracket matching the contents of the bottom or the top, whichever one you factorized. So it turns out this will give minus 1. You can even test it. You can try putting numbers in your calculator, and you'll find that no matter what value you choose for x, 5 sin x minus 2 cos x will always be the negative of 2 cos x minus 5 sin x, and therefore when you divide them, you get a minus 1. The last one is the one that is incorrect. This one is the false one. And the common mistake people make is to look at this fraction, notice that 5 sin x is the same top and bottom, and just cross it out. The danger with that is that you're not following the rules of fractions. We're not dividing top and bottom by anything here. If anything, you're subtracting something from the top and the bottom, so you've got to watch out for that. If that was a valid step, then the next bit would be fine, because cos x and cos x do cancel out. But the issue is in this step here. If you try cancelling things by just subtracting them from the top and the bottom, or just crossing things out when you think it's okay to get rid of them because you've seen them appear in two different places, that's not the same as simplifying or reducing a fraction. So the first thing to watch out for is constant multiples. Here's one thing you might not spot. This fraction you've got here, 2x minus 5 times x add 1 over 8x minus 20 times 3x minus 4. Unless you fully factorize out all the numerical factors, you may not spot that there is actually a common algebraic factor. In this case, 2x minus 5 is hiding within the 8x minus 20, so keep an eye out for that. 8x minus 20 does cancel down with 2x minus 5, but you won't see it necessarily unless you pull out the factor of 4. The next example here we've got is the negative multiples. It's another one that's easy to miss, but just like the 5 sine minus 2 cos and the 2 cos minus 5 sine, we can spot, if we look carefully, anything where the terms are the same but the exact opposite sign. We've got a minus 2x instead of a 2x, we've got a 5 instead of a minus 5. Once you see that, you can pull out the negative as a common factor, and then you can see how most of it is the same as the thing above. You've got to be careful then with the negative. Make sure you either include the minus sign, or you do what I've done here, which is change 3x minus 4 into the negative of 3x minus 4. Looks a little nicer perhaps than having a negative sign dangling around. Notice that because it's an algebraic fraction, it's not obvious whether it's positive or negative number, because it kind of depends on the value of x. Sometimes it'll be positive and sometimes negative. Now, depending on what we want to do with an algebraic fraction, we can often find it useful to split it apart. So, for instance, if I asked you to sketch this curve, that would be quite a challenge in its current form, but I'm going to show you how it becomes more manageable if you can break apart the fraction into separate pieces. So the first thing you might do if you were sketching this curve is to look for x and y intercepts anyway. We can do that straight away before we do anything fancy with the fraction. We find the points where the curve crosses the x-axis by looking at what happens when y is 0, and we find the points where it crosses the y-axis by looking at what happens when x is 0. We get a standard sort of result for when y is 0. Notice here though, when we're solving fraction equals 0, it turns into numerator equals 0. You might want to think about why that happens. If you have a number divided by another number and the answer is 0, there is only one way that can happen. The number on the top of the fraction must be 0, because it makes no difference what you divide by. If you start with something that isn't 0, there's nothing you can divide it by that will give you an answer of 0. The smaller the number you choose to divide by, the bigger your answer. The bigger the number you choose to divide by, the smaller your answer. But there isn't a number big enough to divide and get an answer of 0. It's effectively like dividing by infinity is the sort of thing you'd need to get an answer as small as 0. And infinity is not a number so much as a concept of limit of numbers. So we don't get any sensible solutions by asking what happens when x is 0 or when x is infinity. The only sensible solutions we get for when is this fraction equal to 0 come from when is this numerator equal to 0. Another way of thinking of it here would be multiply both sides by x. And then we get a much simpler equation because 0 times x is 0. So on the left hand side we have x cubed plus 1. Once you've got that, of course, you can simplify, rearrange, solve. If x cubed is minus 1, then we can cube root both sides. There's only one answer to that, minus 1. It's the only number you can multiply 3 of itself together and get minus 1 from. So we now know our curve crosses the x-axis at minus 1. Something strange happens when x equals 0. We don't get anything sensible at all. We get 0 cubed plus 1 divided by 0. And when you try dividing by 0, crazy things happen. Essentially, we have a discontinuity. It's a point where the curve is not defined. We can't put a y-coordinate on it. And this is usually an indication of an asymptote. We've got an asymptote here on the y-axis itself. The asymptote's equation is x equals 0 because that's the vertical line for which the curve is undefined. There's another thing we can look into, and this is the long-term behavior. To give us a proper sense of the shape of this graph, we need more than just here's a point where it crosses the x-axis and we have an asymptote when x equals 0. To get a sense of the long-term behavior, let's look at what happens when we simplify our fraction in a special way. Shouldn't really call it simplify. X cubed plus 1 can't easily be divided by x, at least not yet. We'll learn how we can work on things like that. But what we can do here is sort of divide each separate term by x, piece by piece. X cubed does divide by x. So we can turn this into x cubed over x plus 1 over x. And the x cubed over x does simplify down nicely to x squared. And the remaining part, 1 over x, well, that's a bit more manageable as well. We can think about what happens when x gets very large or when x gets very small. We already know that crazy things happen if x is 0, but what happens when x is 100 or a million or a Google? As x tends to infinity, this is our way of saying what happens when x increases without limit. As x tends to infinity, what happens to y? Well, 1 over a very, very large number becomes very, very small. So y is basically going to resemble x squared plus practically nothing. The bigger x gets, the closer y gets to being the same as x squared. And the same thing happens if x is approaching massively negative numbers, minus a million, minus a billion. We get y is roughly the same as x squared, take away a tiny, tiny, tiny number. So that's interesting. It's not exactly that the curve approaches an asymptote. It's not like a y equals 1 over x curve, where as x gets bigger and bigger, we approach 0. It's more like it's got some of the behavior of 1 over x, the asymptotic approach, but it's approaching another curve. This is what our graph looks like. We can see the crazy behavior on the y-axis. That's the vertical asymptote x equals 0. We can see where it crosses the x-axis when x equals minus 1. But the really cool bit about this is that we can also see the long-term behavior. We don't need x to get very big before the 1 over x component shrinks down small enough that it becomes fairly irrelevant. This is y equals x squared. And you can see already that for any value of x bigger than 2 or smaller than minus 2, our curve, even though it has weird behavior close to 0, very closely matches y equals x squared, provided x is large enough in size. So that's quite cool. You should be able to have a go at a few questions from exercise 7a now. These are the ones I recommend. Essentially, we're practicing some key skills, manipulating fractions involving algebra. This is going to be something that you'll rely on throughout the rest of the A-level course and on and beyond, and A-level further maths and degrees in anything vaguely mathematical or scientific. So it's a really good idea to try to identify your own personal weaknesses or misconceptions in this area as early as you can. And if you feel the need to practice more questions to really embed it, then do as many as you need. This is a good exercise for this. Now, when you moved from GCSE maths to A-level maths, a few things quietly slid into disuse. Mixed numbers was one of them. You don't see me writing 3.5 on the board. I might write 3.5. I'm more likely to leave it as 7/2. Simplified, I'm not going to write 14/4 when I could be writing 7/2, but I won't turn it from a top-heavy or improper fraction into a mixed number, because too much of what we do involves multiplication, and it can be confusing to have a 3 written next to the fraction a half if we don't intend to multiply them. But the division sign is another interesting one. Whenever you've dealt with dividing one fraction by another, for instance, in the past, you've probably used a division sign, but it's fraught with difficulties and ambiguities. Check this, for instance. What do I mean by 16 divided by 4 times 2? Would you get an answer of 8 or 2? You might be very sure of your answer, but there'll be other people who are very sure of a different answer. And the issue comes from the fact that this question in its current form is ambiguous. There is no convention for what we do with this. You might say multiplication takes precedence over division, but that's not necessarily always the case. It's like with addition and subtraction, where both of them are equally valid, and it kind of depends which term you're looking at. At least with addition and subtraction, we can see what to do where. But with questions like this, what does that even mean? Which bit gets divided by what? Are we dividing by 4/2? Are we dividing by 4 and then getting an answer and then dividing by 2? Does it make a difference? Are we going to get separate answers for these? Now, we've got options available to us. We could just throw a bunch of brackets at this, and then at least we would know which bits we're doing when. Brackets always give us priority. Or we could write things in a way that doesn't rely on the division sign at all. We can write them using fractions. So in Excel, you would write it out like this. Not all of those brackets are essential. You can play around and see which of them you could get rid of and have Excel still interpret this the way you think it should. In Python, you would do a similar thing. This is probably the clearest way of actually seeing what it is we're doing. We have 6 times 2/4 divided by 2. This is what I intended by my original expression. You could have interpreted it in a number of ways, but if this is what I intend, then this is the best way of writing it in mathematical notation. But it's not the best way of seeing that number. We want to evaluate it or simplify it, and it might well be that those 4 numerical values are replaced with 4 algebraic expressions, and we want to be able to extend and apply our simplification methods even to the algebraic expressions. Now, one of the really useful things that you may not have done at all at GCSE because you were focused on dividing fractions is to do with multiplying by the reciprocal. This trick is going to save a lot of time and make life a lot easier for you when you're working with big, complicated algebraic expressions where fractions occur within other fractions. The trick is, it's not a new one, it's something you've done with simplifying fractions or finding equivalent fractions often before, but it's going to make our life a lot simpler here. Essentially, we look for the denominators within the annoying inner fractions and we deal with those ones. So think of it in these terms. If we don't like the fact that there is a fraction inside our denominator, or in this case inside our numerator, if we don't want there to be a fraction there, we can choose to multiply top and bottom of the entire big fraction by something which will fix that problem for us. Just like we fix negatives, minus 3/-4 turns into just 3/4, or 2/√3 turns into 2√3/3. We can turn something into a whole number if it was previously a fraction. We just need to multiply by its denominator. So in this case, 4 is the problem number. We have 2 over 4 appearing within the numerator of our fraction. So we're going to multiply the entire big fraction by 4 over 4. On the bottom, we just get 2 times 4. On the top, things cancel out. We've got 2 over 4 multiplied by 4, which is just 2. And once we've done that, the whole thing starts to look a bit simpler. And of course, we could go further, we could simplify down, and we get something significantly nicer. We can see what the value is going to be from this. Now we're going to try an example with algebra. Yes, it should look a little daunting, a little confusing. We've got a fraction within a fraction, and then we've also got another fraction within our fraction, and there are x terms all over the place here. We're asked to simplify this expression to write it in a nicer format so that maybe we have a better chance of making sense of it, or perhaps drawing the graph of y equals this expression. The first thing we do is identify the unwanted denominators, usually one at a time so we don't confuse ourselves too much. We pick out a fraction within the main fraction and we say, I don't want this fraction to be there. And we can always get rid of that through multiplication. We multiply by the denominator and that fraction magically disappears and turns into just its numerator. And the only reason we're allowed to do that is because that term appears within a bigger fraction, and I can multiply the top and the bottom of that big fraction by that same term. So when we multiply the entire fraction by 1, we're going to choose how we write the number 1 very carefully. We'll either write it as x over x, or x minus 1 over x minus 1, or whatever we might need. So in this case, I'm going to notice first that x appears as the denominator of a fraction I don't want on the top. 2 over x, I don't want it. So I'm going to multiply the entire numerator by x, but in order to be allowed to do that and still have an equivalent fraction, I need to multiply the entire denominator by x. You wouldn't necessarily write out every step the way I'm going to do here, but I want it to be crystal clear why this works and what's going on so that there's no fuzzy bits in your understanding. Once we multiply out the top, you see that the fraction disappears. Be careful to multiply everything. 3 plus 2 over x, when you multiply by x, it doesn't just turn the 2 over x into 2, it also turns the 3 into 3x. On the bottom of the fraction, things look like they've got more complicated, but don't be tempted to multiply things out, certainly not just yet. There's no advantage to expanding things necessarily. In fact, often it's more bother to factorize than it is to expand. So if in doubt, keep things factorized until you know that you need to expand them. Now, this is better because instead of having a fraction on the top and a fraction on the bottom, we've now just got a fraction on the bottom, but we could still do with dealing with that one. So next, we identify the problem with that one, which is the x minus 1. That's the denominator of the fraction within our bigger fraction. So we multiply the top and the bottom both by x minus 1. On the top, that gives us now a quadratic. You can see I've still left it factorized. I'm not going to try expanding all of that because there's not necessarily a benefit to it. And having it perfectly fully factorized quadratic is usually better than having it all expanded. On the bottom, I've made sure to multiply 2x by x minus 1. And then the fractional term, we've just lost the denominator. That's the effect of multiplying by x minus 1. Remember, if you do 2/3 times 3, you don't get 2 times 3, you just get 2. 2/3 times 3, the 3 that you multiply by just cancels out the 3 that you were dividing by, and 2/3 of 3 is just 2. So in this case, x times 4 plus x divided by x minus 1, and then multiplied by x minus 1, it's as if you'd never multiplied or divided at all, and you're left with just x times 4 plus x. Now the next thing to do is to try to simplify. The top is fine, that's fully factorized, so I can see the factors of the entire numerator. The bottom, not so much. I'd like to factorize the bottom bit, and if I'm going to do that, then it's going to be helpful to identify which terms are common factors of everything in there. I've not changed anything yet in there, but let's see if we can identify which bits are common factors before because it's quite tempting to expand everything out on the bottom now. But before we do that, look for common factors, and I can see an x there and an x there. So if we pull out x as a common factor of that denominator, we get something that looks like this. It might still look messy, probably messier than the previous line. But what we've got here now is just something linear. We can expand 2 times x minus 1, and then we can add the 4 and the x from the other bracket, and that's a pretty quick process to do. 2 lots of x minus 2, add 4, add x, put it all together, and we've got x times 3x add 2. And what do you know? When we write it out, fully factorized, then we can identify potentially things that might actually cancel, things that are genuinely factors of the top and the bottom of my fraction. And once I've got that, I get a much simpler form. Compare that to what we've got at the top, and there's no contest. This is by far a nicer way of writing this horrible beastie. And you might even go a step further, particularly if you wanted to sketch this graph. It'll be even easier if you now divided through by x and said x divided by x minus 1 divided by x is the same as what we've got. So x over x minus 1 over x. X over x simplifies to give 1. So notice that first term is basically x over x. And then 1 over x is the next bit in there. And 1 over x you can leave written as 1 over x. Just a quick point on your notation. When you find yourself dealing with fractions within fractions, it's very easy to get mixed up. X over y over z and x over y over z sound the same. They even look the same often when you write them down. So be very careful with that. They are not the same thing. You can try this out. If you do 2 divided by 3 divided by 4 on your calculator, depending on where you choose to put brackets or where you choose to embed fractions, those two things will give you very different answers. So if in doubt, include the brackets, and that will make it crystal clear which fraction goes where within your expression. We know that we can divide a factorized expression by any of its factors. If we have an algebraic fraction where the top and the bottom have both been fully factorized, we can identify common factors and divide top and bottom both by those common factors. But what if we can't factorize very easily? What if we're trying to divide a polynomial by something which it does divide by, but we don't know what its factors are? Or, as we're going to get to slightly later, what if we want to divide a polynomial by something that it doesn't exactly divide by? We do this with numbers all the time. We might want to do 36 divided by 5. 5 is not a factor of 36. You could write 36 as a collection of prime factors if you wanted, and you wouldn't find a 5 in there anywhere, so you couldn't just cancel things out. But it might be helpful to have an equivalent to dividing with numbers that leaves you with fractions when it comes to algebra. Can we divide a polynomial by some term like x add 3 and maybe get a nice polynomial result, and maybe get a result that still has a fractional element? We're going to start with the nice exact division, but we're going to look at how we can do this even when we don't have a factorized form for our expression. So let's start with this example. We're told that x minus 2 is a factor of this cubic, 4x cubed minus 9x squared plus 3x minus 2. And we're asked to divide the cubic by the binomial expression x minus 2, a two-term algebraic expression. And I'm going to show you 3 different methods for this. And in general, they each have their advantages and disadvantages. I'd encourage you each time to try each method, maybe a couple of times with a couple of different questions, get a feel for what works well and what doesn't work with each, and develop confidence with more than one method, because you'll find that some questions lend themselves more nicely to one method over another. The first method is called inspection. And it's a weird one, because if you look at somebody's working out for the inspection method, it looks remarkably like they've just written down the answer, because a lot of the work goes on in your head. I'll show you what I mean. The first thing to notice is that if we're going to divide this cubic expression by this linear term, well, the result we get will be something which you could multiply by x minus 2 to get this cubic. So have a little think. I'm going to give you a chance now to pause, if you like, and see if you can figure out what kind of expression you would expect this bracket to contain. So roughly, what would it look like? And can you make any predictions about what any of the terms in that expression might be? Okay, this should be a quadratic. We know that because if you're going to multiply something by something linear and get an answer which is cubic, you're going to need to have an x squared term in there. A quadratic is the most general way of describing an expression whose highest power of x is an x squared term. There's nothing but powers of x in our expression on the left. It's a cubic, which is a polynomial of order 3. It's allowed to have positive integer powers of x and constants. So if you like, non-negative integer powers of x. 2x to the 0, you could treat that final constant as, or minus 2x to the 0. Well, now we know that that bracket is quadratic, we can perhaps start thinking about what we know about how it's going to combine with x minus 2. We're almost working in reverse. Instead of saying, how can we divide a cubic by something linear, we're saying, what would you need to multiply this linear thing by to get the cubic? It's the difference between asking somebody, what is 72 divided by 8, and saying, how many 8s go into 72? In one form of that question, we've switched it round and made it an 8 times what makes 72 question. And you might try some things. Well, I know 8 tens is too big, so maybe we try something different. Let's try 8 fives, that's too small, so we'll go a bit bigger, and so on. We're going to do something similar to that here, but it's not as slow and tedious as you might think. We'll start by noticing this. The only way you can get an x cubed term by multiplying a linear bracket by a quadratic bracket is by multiplying the very first terms, the highest order terms from each. The x term from the linear bracket multiplied by the x squared term from the quadratic bracket. So straight away, you should be able to spot that the value of a in this expression has got to be 4. So the first thing you would fill in there is the 4x squared at the beginning of your bracket. And the next thing that I would normally look at, if I know that I'm dealing with something which is a factor of my original term, there's nothing else going on in here apart from quadratic multiplied by something linear, I'd investigate the constant term next, because it's at the other extreme. The only way you're going to get a constant value when you expand out those brackets is by multiplying minus 2 by c. And if we need the answer to be minus 2, then we know what c has to be. There's only one number that it can be. It's got to be a 1. The next thing I want to look at is a bit of a tricky combination. So I've tried to color code this in a helpful way. We're going to investigate where the x squared term might come from. So on the left, we've got a minus 9x squared. On the right, there are 2 different places where an x squared term can come from. One of them is a constant multiplied by an x squared term. And the other one is an x term times an x term. And we need to look at both. The green bits give us minus 8x squared. Well, that's all right, that's helpful, but we need minus 9x squared. So we actually need another minus x squared. Where's it going to come from? Well, there's another place where x squared terms come from, and that's x times bx. And that tells us that b has to be minus 1. Here's another way of getting the same thing. If we look now at the x term, we can see that now we're looking at the x term times the constant term. That gives 1x. But also we need to investigate the constant term times the x term. That gives minus 2bx. Well, to get a total of 3x, we need 1x and another 2x. So in order to get 2x, we need b to be minus 1. That's the same result we got from the last one. So it should fit with both. We can have minus 8x squared minus another 1x squared, or we can get our x minus 2 times minus x. Either way, we end up with a 3x. That middle term is the most confusing one, but I think it's helpful to look at both the x squared and the x terms when you're doing something like this, because it gives you a belt and braces approach. You can test and make sure that your result works, that it fits from both directions, if you like. And if in doubt, you could multiply out those brackets It doesn't take ages. You'll get 6 different terms because remember, when you're multiplying brackets, you multiply every term from each bracket by every term in the other brackets. So there'll be 6 different terms before you simplify. One of them will be the 4x cubed. One of them will be the minus 2. There'll be 2 x squared terms that should simplify together to give minus 9x squared. And there'll be 2 x terms which should go together to give positive 3x. And that's inspection. That's how inspection works. You basically look at each part and you work out what the terms would have to be within the bracket to make it work. It feels a little confusing, I think, when you first come across it, but for relatively simple examples, it's probably the quickest of the 3 methods. You should have a go now for yourself. X minus 6 is a factor of this cubic, 2x cubed minus 15x squared plus 14x plus 24. Therefore, you should be able to divide that cubic by x minus 6 using the same approach I've used here. Look for the x squared term first, look for the constant term, see if you can figure out what's going on in the middle to make the x squared terms match and to make the x terms match. Pause the video, have a go at that, and then check back to see if you've got the same answer as me. Here's what I have, 2x squared minus 3x minus 4. And you can verify that if you multiply it out by x minus 6, you should get back to the original cubic. Method 2. I'm going to use the same example so that you'll start to see similarities and see where the same numbers come from. And because it's doing the same job, it's just a different format for the same technique. You'll see that the maths behind it is very similar as well. The first thing to notice is that we're trying to make a multiplication again, so the inside of our grid will represent the cubic we're trying to break apart. We do it by splitting it up like a multiplication grid. We're going to have x minus 2, which combined gives us the number we're trying to divide by. And then everything inside the grid will correspond to 4x cubed minus 9x squared plus 3x minus 2 once we're done. The column headings, they're the things we're trying to fill in. That's what we're interested in. We're trying to find out how many x squareds, how many x's, and how many constants we would need in order to generate for ourselves within the table all of the terms of the original cubic. So x minus 2 down here on the side is the divisor. It's known as the divisor. It's the thing that we are dividing by. Once you start having names for these things, it gets a lot less confusing. The first thing we can fill in is this term. This term goes in the top left corner because it is the highest power of x. And if we're having x squared terms in the first column, and then x term in the second column, and then the constant term in the third column across the top, then we know that we're going to get the highest power of x in the top left column, top left box of the grid. Now, once we've filled in that box, we can actually fill in the box above. We now know the column heading, because the only way you can get 4x cubed by multiplying x by something is to multiply x by 4x squared. So we've got the first part of our quotient, which means the bit we get when we divide. But now we've got 4x squared, we can fill in the bottom bit of this grid. 4x squared times minus 2 gives minus 8x squared. That is beginning to contribute to the minus 9x squared that we want for our original cubic. We're trying, remember, to make the 6 cells in the middle of this grid combine to give exactly the cubic expression above. But minus 8x squared is not enough on its own. We need to have another minus 1x squared so that altogether we've got minus 9x squared. And luckily, there is another space on the grid that is going to provide for us an x squared term. We've got one term here from a constant, minus 2, times an x squared term, 4x squared. But we'll have another x squared term appearing when we have an x term times an x term. This is in fact just moving up diagonally through the grid. So this place is going to have another x squared term, and it has to be minus x squared because we need those two terms together to add to make minus 9x. And in fact, this diagonal you'll see going through the table, and even for bigger, more complicated questions, you'll see moving along this diagonal is a way of increasing the order of the divisor, so we go from the constant term to the x term, while decreasing the order of the terms in the quotient. We go from the x squared term to the x term. We can see here we need a minus x. It's got to multiply by x to give an answer of minus x squared. And now we've got that column heading. We can multiply it by the row heading to get the value at the bottom of that column, 2x. And then we move up the diagonal again. 2x is part of what we need for the linear component of the cubic at the top. We want a 3x, and we've got 2x so far. We're going to need another x. These two terms combined should completely give us the total number of x's in our original cubic expression. But if that top term is x, then there's only one thing that we can have in the top of that column. It's got to be a 1. 1 times x gives x. And of course that means we can fill in the final term. We can check to make sure that number is the one we want. Because we've not got any more flexibility here, there's only one way to get that constant. The nice thing about this grid is that it puts on a slightly more formal setting the process that we did in our heads when we do inspection. So if you found inspection a little bit hard to grasp, you might find the grid method with its nice logical layout and its procedural setup. It's quite a nice way to work through the same process and generate the same results in a slightly more formal way, so you're not having to hold everything in your head all at once. So remember, we call this 4x squared minus x plus 1 the quotient, and that's the thing we were working towards finding. If we were asked to divide the cubic by the linear expression, the result will be a quadratic, and this is the quadratic we're trying to find. So we can say that if we divide this by this, here's our answer, 4x squared minus x plus 1. Again, with the same example for yourself, I'd like you to have a go at using this method. Try the grid method to divide that cubic that you had before by x minus 6, just like you did before. You should get the same answer at the end, which for the record is 2x squared minus 3x minus 4. And the method should feel similar because the numbers that come out and the things you're working out as you go along will feel the same. But hopefully it will give you a feel for how the grid method works. The third method I want to show you, the final method here, is going to use the same example we had before, 4x cubed minus 9x squared plus 3x minus 2 divided by x minus 2. But this is the more traditional approach. This is what you'll normally find in the textbooks, and it probably resembles most closely long division that you might have done with numbers back in high school, potentially. We set it up like a bus stop division. So this is what it always used to be called back when I was teaching in secondary schools. You write the number that you intend to divide, and then you stick it inside a bus stop. So it's got a vertical on the left and then a horizontal line across the top. Then we write the divisor to the left. So if we were doing 1,000 divided by 7, we'd put the 1,000 inside the bus stop on the right, and we'd put the 7 outside the bus stop on the left. And then the result will eventually show up above the line. So we've got a horizontal line at the top, and our result should be a quadratic that appears above that line. And we begin by choosing a number that will help us to get the 4x cubed term at the beginning. So we start by focusing, like we have with many of the others, on this highest power, the 4x cubed. And we say to ourselves, what would we need to multiply x minus 2 by to give me 4x cubed? And the answer is 4x squared. That would do it. Well, now we've decided what the largest term in our quotient would be. We work out what would happen if that was the only term in our quotient. We multiply x minus 2 by 4x squared, and we see what we would get. Hopefully, if we've done it right, we'll get a 4x cubed, but we'll probably get some other stuff as well. So this is what it comes out as. 4x squared times x is 4x cubed. 4x squared times minus 2 is minus 8x squared. So that goes in the next column along, if you like. We can see how it lines up with the minus 9x squared that we were hoping for. So it's not quite what we want, but it's unlikely that we get perfectly what we want for two different terms. We were focusing on getting the first term to match. We can worry about the second term later. What we're going to do next is we think about what this bit gives us. We need to get rid of it to see what else we need. We've already found a way of generating the 4x cubed term and some portion of the x squared term. If we subtract that red stuff from the line above, so we rule off and we take away, that will tell us what's left. 4x cubed minus 4x cubed should disappear. If you've chosen the term right at the top, then that first bit will disappear. And we're left with, be careful with your signs here, minus 9x squared, take away minus 8x squared. And that will leave you with minus 1x squared. This is effectively the remaining x squared term that we're going to need to find somewhere, because we've already found minus 8x squared, but altogether we need minus 9x squared. And then we repeat the process. So we look now at how we can generate a minus x squared term. So our focus now is on this. How can I get a minus x squared term by multiplying x minus 2 by something? Well, what if we multiply by minus x? That would do it. Minus x times x will give minus x squared. But of course, we will also introduce for ourselves a minus x times minus 2, which will give a plus 2x. And we do the same thing again. We rule off and we subtract. So minus x squared take away minus x squared will perfectly cancel out, as intended. 3x take away 2x will leave us with x. And we still have this minus 2 because we've not managed to get any constant yet. So we still need to contribute an x, and we need to contribute a minus 2. Fortunately, this bit looks pretty straightforward, but I advise you to continue until the very end, even though you might feel like we don't need to go much further. We can see that we need a 1 here because we need 1 times x to give a value of x, and we'll also have 1 times minus 2, which happens to give us exactly what we need for that second term. It's not automatically a given that you'll have exactly what you need for the last term. It depends on us knowing that x minus 2 is a factor of the cubic. We're going to look a little bit later at what happens when you're dividing by something which isn't a factor, but it's a very similar process to this with just a slight change at the end, because we still rule off and we still subtract. But in this case, we get a 0. In other words, there is no remainder. We've managed to divide perfectly and exactly, and there's nothing left over. So this number down here should be 0 for the questions I'm going to set you in a moment, because in each case, the thing you're dividing by is a factor of the thing you're dividing. But when you get to questions where you're dividing by something which isn't a perfect algebraic factor, there will be a non-zero remainder at the end. So get into the habit of doing this in full and getting a remainder of 0, and then you'll be able to apply this same bus-stop division method when you've got remainders involved. In fact, there are ways of adapting methods 1 and 2 to deal with remainders as well, and we'll cover those when we talk about remainders. Again, this gives us our final answer. If we divide the cubic by the linear expression, we get for ourselves this quotient 4x squared minus x plus 1. And you can try this for yourself once more. Use the same one so you can see how the method works with your particular cubic divided by your linear divisor. Remember, you should get the same answer, 2x squared minus 3x minus 4. And if you try a few of the questions I set you using some method and try some of them using a different method, or if you get stuck on one where you find one method is too tedious or too confusing to hold everything in your head, then switch across to a different method. Typically, the more formal methods, like methods 2 and 3, are helpful if you're dividing something that's more complicated than a cubic. If you've got a quintic or a quartic, that is an order 5 or order 4 polynomial, and there will be some of those in the book, then you might find it more helpful to have a more formal method to follow step by step than try to do everything through inspection. So these are the questions I would recommend from exercise 7b. Just a handful from questions 3 and 4 should be good ones to work on here. I don't want you doing loads and loads and loads of them, because we're shortly going to learn, as you can see from the top right of the screen, we're going to investigate factor theorem, and we might even talk a bit about remainder theorem, which gives us a quick and efficient way of identifying whether or not something is a factor of a given polynomial. When we've worked on that a bit more, we'll be able to revisit some of these questions and find other useful ways of dealing with them.